Good afternoon and welcome back from lunch. Avalanche detection is something new to me. There's no doubt about it. And it's been around for a little while, but the technology, radar technology, is improving pretty quickly. And with it, we're seeing new applications. We're seeing great researchers coming up with new solutions that I think have huge potential for globally, but especially in North America, where we really haven't gotten our feet wet with it. Our first two talks really go together. Walter, I will butcher his last name, even though I've said it a dozen times, Steinkogler, I think. Did I get it?
Pretty good.
Pretty good. Rolling Stone, apparently, is what it really means. The rock star. Walter's got a deep history in the Avalanche game. He got his master's degree in meteorology, and then when he was at the SLF, got a PhD in civil and environmental engineering. Since then, he's moved on to work with Wyssen Avalanche Control, primarily in Austria and in Canada. This morning, Walter kind of reminded me why we're all here, and he's got a deep ski bum at heart. We first started talking last January, and he was deep in an avalanche course through the CAA and just couldn't wait to finish just to go skiing at Rogers Pass. Walter.
Thanks, Fred. I hope you all guys had a good lunch, because you're going to need it. Because I want to take you in an imaginary way on an avalanche control program for like a typical day work. I guess it's this one, right? We're talking operational radar and infrasound systems for avalanche detection. Kind of the first word there is pretty much the most important take-home message from my talk: operational. This stuff works, it's in place, and we run it. Before I start here, I can give you a general overview. I will not go in very deep details. Lorenz is going to catch up later on with an example of a radar application. I give you a broad overview, and with that I want to thank our partners first here that provide the technology and that work together with us, and also especially our clients, which are also kind of our partners, and they are providing the most critique, which we like usually, all the way all over Switzerland up to Norway. So thanks a lot to all these guys and girls. Avalanche detection. Why at all, right? Coming back, that I want you to imagine you're part of an avalanche control team. It's in the morning, and your task is, you have a road to a ski resort or to a town, and your task is to protect this road, mitigate the risk, the avalanche risk and the hazard there. You have racks installed from whatever system, there are multiple out there, and you bomb. You got confirmation that the bombs went off, but you might not know what happened actually, what did you release. And this is kind of the idealized thing, and we are sitting in a warm room, but this is not real life, because real life looks like this, right? It's in the middle of the night, it's 5 o'clock in the morning, it's snowing, you're standing on the road, and all you see is nothing. Because you're standing down there, you initiate your rack system, but you don't have eye on the mountain, right? You need a third eye that tells you what was going on up there. So, and that's why we want to have avalanche detection systems, right? We want to verify the success of the preventive avalanche release systems we apply. And the second part is, with these systems, or with many of them, we can also detect natural avalanche activity, so they monitor these paths all the time. I will not talk about automatic closures of traffic lines. This will be in the next talk. And yeah, coming back to this overview. You see our access road. You see there is Lara, Ida, Sarah. These are our girls, right? It's all girls' names. We like our girls. And so Lara and Sarah, these are the radar ladies. Lara is the long-range radar. Sarah is a short-range radar. And I want to show you a few examples now. This is not really a typical avalanche, it's more an ice fall that breaks off. On the left hand, you see the, yeah, it's moving good. So you see there's an ice fall breaking off, and this is how the radar pretty much sees it. It's like a band, monitoring band over the mountain, and this is how it captures the motion of this mass of ice that moves down the mountain. Sarah, very similar from a technology point of view, but she lives in a different place. She lives, for example, on our magazines on the top, and she monitors the release area pretty much, right? You might have an application where it's fine for you that you only monitor the release area because everything that you release will end up on the highway anyway, or your railway or whatever. So she is doesn't have that distance view, but it might be sufficient for certain applications. But this is Sarah. We also got Petra. She monitors something different actually. It's the same as Sarah pretty much, but she monitors people. And on the top part, you see top right is the radar visualization, top left normal image, lower right thermocam. And you see the top right, you see it tracks emotion there, and you can already see the guy coming up with a ski touring hill, typical one, and you can see the guys moving along there. Why do we do this? We're not bombing this slope, we're bombing the other side, which is really steep, but the problem is on this flat spot where you see the people walking, they hike up there in the middle of the night, avalanche danger 4, doesn't really matter, they always go, so we try to avoid bombing people usually. And so this is another guy, he walks there with his dog, it's kind of neat, it's kind of Big Brother style a little bit, but yeah. So it gives the guy who presses the button confirmation that nobody is up there. So also this you can monitor with radar technology combined with, we saw applications of thermal cameras before. This is kind of the system that we have running there. So these were the radar ladies. We also have, on the picture you see Lara and Sarah in the orange here, but there's also Ida. Ida lives down in the valley, and she monitors a bigger area. She listens usually. Ida is an infrasound detection system, and infrasound is something that we cannot hear. It's generated pretty much by the powder cloud of an avalanche when it pushes the air away. Then it generates sound waves that the Ida can detect. With that being said, it's typically it needs to have a certain size. You need to create a powder cloud to really create these waves very nicely. Wet snow, I'm going to show an example. It pushed the system a little bit to the limit, but it works pretty well for dry powder snow avalanches of a mid-size. Just to get you a bit the concept what you're measuring. Yeah. Here an example, how does it look like in an operational sense? You pretty much have an overview. These are two EDA systems next to each other. Blue would be rack systems. And EDA can tell you, it monitors the natural avalanche activities, here shown in green. It monitors explosions and can associate to these explosions the controlled avalanches. And she does that day and night, 24/7 pretty much, which is pretty nice because you can get the activity, right? I mean, you are there, it's again middle of the night, you get there in the morning, 5 o'clock, and you can look what was going on in the last few hours, where am I? Is like, are my indicator paths already running? Is the avalanche activity increasing? And it gives you an indication where this avalanche is released. I mentioned before that it works, for example, EDA works very well for mid-sized avalanches, dry powder snow avalanches. We are running pretty extensive verification campaigns on all our detection systems because it's kind of important to know where our limitations are. We know where it works really well, and now we want to push the system. And what you see here is these are all recorded avalanches, not recorded by EDA, but recorded by a person in the field actually. And it's dry ones, wet ones, all different kind of sizes. And we, this helps us really to understand better our system and where our limitations are. Because I can always tell you, yeah, it works, but where does it work, right? And to which, does it fit to your application or your operation actually? And yeah, it's kind of important to know this. Here's an example. Yeah, this is actually should be a video. This is a big avalanche back there, basically, size 4 maybe. And at some day, Ida pointed us in a direction, in a really weird direction. We said, okay, that's an error, whatever. And then a guy called us a day later and said, yeah, we had a really big avalanche there, and it's like 14 kilometers away that Ida detected. It's not the typical range that we say it operates in, but it's just to show you a bit the upper limit. This is a decent-sized dry powder snow avalanche, so it generates quite nice infrasound waves. On the other hand, we had some, to also show you the limitations, and I mentioned the wet stuff, which is typically not doesn't have a powder cloud. We had them run pretty close by the EDA, really wet stuff as you can see in the spring, and it did not automatically detect them, but interestingly enough, some of the algorithms in EDA detected even those. So in my opinion, this might take a while, but there is also some possibility to increase the algorithms. Maybe we also can get for wet snow avalanches. But generally, EDA works pretty or very good for especially dry snow avalanches. Quick summary here, just very brief. I think these are some really just indicator numbers which I think are important. Two important ones that everybody asks all the time is what's the operation range of these systems? If you look at Lara, for example, operates up to 2 kilometers, and the size it still can detect is like small avalanches, size 2, size 1. Infrasound, on the other hand, typical operation range is up to 5 kilometers. We saw the example of 40 kilometers. That's the one farthest away at the moment we detected. And it works very well for mid-sized dry avalanches and larger. It works also good for smaller ones, but we are still, smaller ones, I mean the ones we bomb, right? This is a small avalanche. But we are still, running our verification campaigns to see how far can we really push the system there. It's crucial to know what your system can do and what it cannot do. I showed you all this stuff now, but you are still standing on your own and you still don't see anything, right? What does that mean for you now? All this different technology we have out there. How does it work for you? How do you incorporate this in your operation? And I want to show you here an example of how we picture it, that this needs to be incorporated into a daily operation business. This is an example of an avalanche path in Switzerland. Probably, it's, as you see, a big open bowl on top, funnels everything into one gully, goes right to the highway, also endangers the railway and the hiking trail, but that's easy to block. But the railway pretty much tells these guys, I give you 30 minutes, unless it's a catastrophic situation, I'm not going to change my plan for you guys. So they have a very tight schedule, right? They cannot block this thing for 2 hours and say we do avalanche control now. So what they have there on top of the ridge, there are some avalanche towers. We have some geophones, the 3 orange circles in the path, and we have 2 Lara radar antennas, which is actually still the old version. The new version sees 90 degrees actually. And what is going on here? If you look here, it's 5 minutes before 5 in the morning. The picture we saw. Pitch black dark on the road and it's snowing. You shoot your first tower, it tells you a few seconds later that the geophone detected motion in the upper area and the avalanche is even detected by the radar until the very end. What does this tell you? You initiated with 1 tower an avalanche that triggered both geophones, went over the bench into the gully. It's a decent sized avalanche you just triggered, right? So you know, okay, I mitigated the avalanche hazard in this area pretty well, because otherwise it wouldn't run that far. Then you keep on shooting the other towers through and you work your way through, and by the time you shot all towers and you got confirmation that you also released an avalanche, it's 5:10. So the whole program here, shooting I think 9 towers in total, or whatever it is, including confirmation of detonation, including confirmation of avalanche, took them 15 minutes. And this is even the old control system. So with the new one, you're even faster there. So this is how we picture that you need to incorporate all these detection systems into a very intuitive, easy to use platform. Because you cannot be standing there and looking at 5 different programs and websites. You don't have the time for that, in my opinion. At least nobody of the guys that I know that do this job have the time. So to sum this up, really, from an operational point of view, what are we aiming for with detection systems? It's really the reduction of closure time, right? I shoot, I know what I released, I can open again quite fast. It's also a reduction of residual risk. If I cannot see anything what I released, I bomb. Maybe I hear the rumble of an avalanche, maybe not. Did I release it? Yes, maybe not. I don't know. Did I reduce my residual risk really? Well, that's up to you if you want to interpret this. Detection systems allow you to open your road with much more confidence. And this needs to be incorporated into an integrated platform. Ideally, you have one platform where all of this stuff is on. You control your system, you control your road closures, you communicate, you have detection systems, everything in one platform. It needs to be fast. Time is crucial. The guy back there, by the barrier, they are using their horns, open up, I need to go to work or whatever. And you need to have a clear communication. It's not just, you must not need to spend a lot of time to interpret these results. It must be clear, fast, and efficient. And yeah, this is my take-home message from our ladies. And yeah, they are just waiting for application. Thank you very much.
Thank you, Walter. Any questions? Oh, yeah.
I'm just curious how Sarah deals with wind-driven rain, whether she likes it or not.
That's for sure would push it to the limit. When you imagine a really wet snowfall, like you have big flakes that are surrounded by a wet snow film, if you want to call it like this, that pushes the radar to the limit. But we are still trying to find out actually. That's one of the limitations for sure for the system, probably. But I mean, what's your experience up in Alaska? You might have this situation.
No, we don't think Sarah deals very good with wind-driven rain, and unfortunately we have some experience with that.
Yeah. I can imagine that. Yeah.
And we also have some experience with single geophone installations.
Mm-hmm.
They love to see small earthquakes.
Oh yeah, that's for sure.
And it's hard to set the threshold on the geophone small enough to see avalanches and filter out the earthquakes, but high enough to filter out the earthquakes.
I think for the geophones, unfortunately Alec is not giving this talk about the seismic stuff now, because it's quite easy actually to get away from just a threshold-based alarm, because an earthquake has a very different signal than an avalanche. And you can identify very well, this is a truck on the road, this is an earthquake, this is an avalanche. So this is more on the signal processing side. But that's quite easy to handle. Wet rain is much harder to handle than earthquakes. There's one.
Got it. Bill, Allie here.
I have a question about Ida. And where are her sensors located? And what are they on the ground? Are they in the air? Or how many typically do you need?
Yeah, I didn't really go in detail there. It's usually a sensor array of 4 sensors, around like 150 meters apart from each other. They're on the ground, ideally covered by a bit of snow. This filters out a lot of noise that we try to avoid anyway. And best thing I would say, I mean, Giacomo is also around the guy from E10. I recommend also that you talk to him then. Ideally, you are somewhere in a forest, actually. So snow is good, forest is good, and yeah, like on the other side of the valley, a little bit further down. That's the best setup you can have. And there are different ways to run EIDA. We have 2 versions. One is normal sensor, the other one is very sensible sensor. One runs with electrical cables, the other one runs fiber optic. So it really depends on your problem and your location, how to best set up EIDA system. But this is pretty much 4 sensors, 150 meters diameter.
Any more questions? Okay. Our next presenter, Lorenz Meier, is going to take this application a step further. Lorenz is a physicist. He was at the 2010, I might get the story a little off, but he was at the 2010 ISSW in Tahoe, and I believe was giving a paper on radar. Somebody asked a question, well, what about it going operational? And that triggered an idea. So he bailed on his job at the SLF, started Geopraevent, his company, and now has an operational radar system that he's going to discuss. Lorenz? And I like to think that's a perfect application of research and practice.
Thank you. So I'm going to talk about an operational system that we are running in Zermatt, and that closest to road with radar in real time. But let me first show you a few fundamental things about radar. And also maybe the talk I had during 2010, that was my last ISSW that you mentioned, where I got the question when those systems would be operational. So I didn't attend any ISSW anymore since then because I was busy setting up Geopraevent. Now I have time. So just shortly to tell you what we do, we install and we develop, install and operate electronic detection systems for natural hazards, meaning we place sensors somewhere up in the mountain. Sometimes it's radar, sometimes it's other sensors. We have usually some alarming system, and we control all those systems remotely from our servers to be sure they're working all the time. We are doing that with a number of natural hazards. I'm talking about avalanches, snow avalanches here. You heard Stefan Magens talk maybe on Tuesday about glaciers, so that's the location actually he mentioned. We are looking at the reflows, at water, and we also detect people. I'll come back to that shortly. Why do we use radar? There has been presentations about thermal cams on Tuesday. The big advantage of radar is that you can see through fog, through snowfall, and through rain. With a normal camera, you can have a good overview on your terrain on a sunny day, but already at night you don't see a lot anymore. With a thermal cam, or also with a laser, it's an active system. You can monitor your area at night as well, but the performance in bad weather situations is very limited. With the radar, you can penetrate fog and that bad weather. And since the systems that need to close a road in real time, they have to work at any weather conditions, because right at bad weather, that's when they are needed most. So the advantages of radar, besides the good weather capabilities, are that you see a large area. You can monitor several square kilometers with the radar. Ranges are up to a few kilometers, and you don't have to go to the area that is endangered. So you don't have to go into avalanche terrain to mount some sensors. But it's also less prone to damage. It's less dangerous to install something. We are using two different radar principles for our project. Just briefly show you this one as well. Interferometric radar is going to be mentioned in a few talks as well. We are looking at slow movements with interferometric radars, millimeters per minute or even per year. So that's movements of rock instabilities of glaciers. This is a glacier that we monitor since 2 years continuously. Every hour we get this kind of plot, and we see if some parts of the glacier accelerates, and usually a few days later they fall off. That's what Stefan Mayer told on Tuesday. For the systems I'm going to talk about now, we use Doppler radar. So with Doppler radar we measure fast speeds, we measure rocks falling down, or we measure avalanches. So these are used for alarm systems. And we call systems an alarm system if the system itself takes action, meaning closes a road without the intervention of an expert. How does Doppler radar work? Jan Thomas showed that very nicely on Tuesday, and just briefly go back to that. We send radar radiation on a target. If this target is not moving, the radiation is reflected and the frequency is unchanged. However, if the target is moving, the frequency changes and we can see a moving object by that. And as I mentioned, this works as well when there is fog or rain or snowfall in between your radar and the person. Now, how does the radar see an avalanche? You remember that from Walter's talk? I just show you briefly what happens here. This is the digital terrain model. This is the Wyssen 4,000 meter high peak. And our radar sees a 90-degree opening angle, so horizontally we see a lot. Vertically we see about 10 degrees, so we see every movement here in this area between 1,500 and 2,000 meters. And as soon as something moves, we can visualize this movement here, what kind of an activity that the radar notices. And as soon as the movement is below the radar antenna, so on the end of the avalanche is now below the radar, so we don't see it anymore. So we have to make sure we cover the area with the radar that we want to monitor. The radar can also see people. This is from an operational project in Zermatt, where they're doing avalanche control, and they want to make sure that nobody has entered the area prior that they do their work, so they don't bury anybody with the avalanche that they are going to trigger. We have up to now installed about 15 radars. By the end of the year, we have detected quite a few avalanches in the last 2 years, so this helps us a lot in adjusting and optimizing our software release. We also have 2 projects where we're detecting rockfall. We've detected 1 debris flow because they're not that frequent, luckily. There's 2 geometries that we use them, looking upwards from the valley down upwards to a mountain, or we put them, for example, on a Wyssen tower and look down. So now let's turn to Zermatt. I'd like to show you that example a bit more in detail. This is the town of Zermatt. You might know the Matterhorn here. And there are 3 avalanche paths here that threaten the road that goes to Zermatt. So it's the only road going up the valley. They have about 200 cars per day, so quite some traffic, considering it's a car-free village. We're all parked somewhere here. And they asked us if we could provide them with a radar solution that closes the road here in real time. So what did we do? We placed 2 radars on the opposite side of the valley, one monitoring this area, the yellow one, and another one monitoring this orange area. As soon as this is about 2 kilometers from here to here. As soon as we see movement here, the radar analyzes the data in real time, and if it considers that's an avalanche and that the avalanche is large enough to potentially reach the road, it closes the road here with 4 barriers and 5 traffic lights. So there is 2 locations where the avalanche can overflow the road, and that's closed immediately. Now it's well possible that the avalanche stops here somewhere in between, and if we don't measure it with the lower radar within a specified time, we know that the avalanche didn't continue further down. We can then automatically reopen the road again. Currently they do it manually, but it would be no problem to do it automatically. Another reason for the lower radar is that wet snow avalanches can start somewhere here in between, and we still need to close the road for them, so they might only be detected by the lower radar. And just to show you where we detect the people, that's not far away, that's 4 radars that are back here. I'd like to take you now on a journey to Zermatt. There is a 3-minute movie that the international section of the Swiss TV did on that system that shows you nicely how it looks like and also how the local people there work with it.
The access road to Zermatt is flanked by steep mountain slopes and in the direct path of potential avalanches. When there's a high risk, explosives experts go up in helicopters and throw charges at the unstable snow layers to set off avalanches. That's routine work for Stefan on the mountain. He does this about 300 times every year.
We have a large area prone to avalanches. It has a 2.5 kilometer long potential line of breakage. In a situation like this, it's generally better to proceed with a conventional method of controlled blasts, since you can see in which direction the snow has piled up after the explosion.
To keep avalanches in check, besides these tried and true methods, Zermatt is breaking new ground in terms of monitoring and sounding the alarm. At 1,800 meters above sea level, high above the entrance to the town, an avalanche warning system has been installed. It's the first of its kind in the world and uses radar technology to monitor the start of avalanches. The system was devised by Geopraevent, a company in Zurich. Here, the system is monitoring a 2-kilometer portion of the opposite slope.
Our system uses a similar principle to the kind of radar that detects speeding cars. We send a radar wave towards the mountain, and if something starts to move, we receive a signal.
Once the signal is received, the system evaluates the data in real time. If an avalanche is detected, the road is immediately closed automatically.
With the uppermost radar, we monitor the higher portion of the mountain, up to about 2,400 meters above sea level. This system tries to detect an avalanche as soon as it begins, since we only have a very limited amount of time to close the road below.
These images from a year ago show what an avalanche would look like. This avalanche was artificially triggered. It reached the road below. Since the radar system has been put in operation, there haven't been any avalanches of this magnitude. Nevertheless, Zermatt has been able to correctly detect a few smaller ones.
Yesterday morning, for instance, there was an alarm at 8:24. We could instantly see where it was developing and observe how it broke below the Weisshorn. The avalanche wasn't in the range of the lower radar, so no emergency measures were triggered. Thanks to this information, we could correctly evaluate the risk and decide to open the road again. We were able to raise the barriers directly from our desks.
So let's turn back to the radar. We have 2 radars. One monitors the upper portion of the slope. The lower one is more or less looking horizontally across the valley, and it monitors the lower parts. And just to visualize that again, I show you that avalanche once more from 2015. So you see how the avalanche enters here this radar band, and that's roughly the time when it's detected. Now the system needs to decide instantly if the road needs to be closed or not. With that big avalanche, of course, that's an easy decision. The road afterwards looked like that. So the radar cannot prevent, obviously, that the road is closed, but it can prevent that the car is here. So how does the system work in detail? The first step is that the avalanches need to be detected in the radar data, so there's a lot of algorithms behind that. Wet snow avalanches look different than dry snow avalanches, so we have acquired a lot of data to make sure that all kinds of avalanches are detected by the system. And it needs to decide if the avalanche is large enough to reach the road. Then the road is closed. There are fiber optical cables running from the detection system to the barriers, and as a redundancy we have radio connection as well. And then the locals get alerted by messages, and they log in, check online where the avalanche was detected. They can check webcams as well to see if the road is covered by debris. There are 4 webcams with infrared lights for night vision along the road. So then they can open it quickly, and they do that on a smartphone or from a computer, because reopening quickly is really key here. We will close the road a few times, I'll show on the next slide, without an avalanche having hit it. And if the road is closed for too long, people will start ignoring the traffic lights, and then the system is of no use anymore. So we have here a small statistics from last winter, how many minutes it took the authorities to close the road again. First time here, that's the time between closing and opening. First time it took more than 20 minutes because they had to get used to the system, but you see how they continuously improved. So by the end of the season, the road was usually closed between 5 and 10 minutes until they reopened it again. Here is a few numbers for this first operational winter. We have detected 417 raw events. That's the events that passed our first filter stage. Then after the second filter stage, it was 27 that we identify as avalanches. There is a lot of motion here because the heliport of Zermatt is right below the radar. So we have tens of helicopters crossing our radar beam every day, and we need to make sure we don't close the road for a helicopter. Otherwise, the pilots, I guess, will start the competition that who closes the road more times. So we have 27 avalanches, and 15 of them were blasted ones. So we didn't close the road when they did blasting, because we wanted to test the system, of course, for that kind of event as well. Of those 27 avalanches, the system considered 24 as being large enough for road closure. We didn't have any huge avalanches last winter. There was slow wet snow avalanches at 20 kilometers per hour, average front speed to 80 kilometers per hour for the bit larger one. Now, none of the avalanches reached the road, so you could argue, well, that's 24 false alarms. My opinion is that if the avalanche, or if what triggered a road closure is an avalanche, and the locals would close the road as well by looking at the avalanche. And we did check every 24 of these with the locals, showed them picture, showed them where it released, and they agreed that they would have closed personally the road as well for those 24 cases. So I don't consider that false alarms. We didn't have a single road closure that was not related to an avalanche. So not by helicopters or by anything else. So my conclusions, the real-time detection of avalanches on a large area with these 90-degree horizontal opening angle radars works operationally. The radar has to decide very quickly on whether the road needs to be closed or not. When the avalanche is still high up on the mountain, on about 2,400 meters above sea level, the road is on about 1,600 meters above sea level. So there's 800 meters in altitude difference. And fast and an easy reopening is really important, because we will close the road many times more often than there actually is avalanche debris on the road. But it can be reopened automatically by this second radar. Currently, that's an issue of regulation, if that's allowed or not. So the Zermatt authorities, they would like to have the automatic reopening, but the state, the canton of Wallis, they don't allow that yet. An outlook, we are currently improving the algorithms for other mass movements, rockfall. We have 2 projects running on that, and also the brief. Thanks, and I'm looking forward to